Yeah, thank you, Mike, for the introduction. Apologies for my harsh voice. I would like also to congratulate the French team for setting up this seminar, the web seminar, also for drawing a sizable audience, behind that. Also for dealing with difficult people like myself, who is late in submitting the abstracts and all that. Michael asked me indeed to address, present, something very general in digital twins, and the initial title has been a bit too general. So there was a danger to have to lose substance, you may wish, with such a too general topic. So we try to bring more focus, on digital twins, with an emphasis on bioreactors. After all, this is the priority of Bioindustry 4. Okay, so before I go any further, I would like to dedicate this presentation to Giuseppe Perugino, an excellent colleague and good friend, because, above technologies and projects, people matter. So I would like to, express my condolences to his family, apparently, and very close friends of his, from Italy. Now, digital twins is a very popular topic, and apparently with a lot of references to knowledge, intelligence. So by means of inspiration, you may say, by means of reference, I would like to warm up the audience with some famous quotes from one of my favorite references as a scientist, Richard Feynman, pioneering computing, quantum computing, before even computing was shaping up. But here we remember him as he tries to define these difficult kind of concepts of knowledge, of intelligence, of wisdom. Also, as he tries to unfold, you may say, a desired position for engineers and scientists, as to their knowledge pursuit in life. But Richard has not been the one who introduced digital twins. The two congenial, figures from NASA back then, research scientists in around 2000, they have introduced this topic at the product life cycle management conference. The definition is what you see there. It's pretty general, you may say, related to hydrogen tanks, and the concept there was very simple. And the digital twin had to consist of three entities: the physical entity, the virtual entity, and the data connection between these two. This is something we have carried over in all these other applications, but apparently this concept became very popular as it has involved or emplaced very straightforward applications in simulation. People who were doing simulation could claim, a different word for what they were doing, communicating with the experiment, the physical process, upgrading their simulation into different words apart from digital twin, the virtual test beds, and similar stuff. It has been a lifeline and it is a lifeline for CFDs. But as it is straightforward to embed data into models, it is much more difficult to define more generic concepts. So Michael Greaves, now 10 years later, or now as the CEO of a dedicated institute for digital twins, realizes all that. And in this kind of reference you've seen underneath, he summarizes, the developments. He admits, progress in information technology, in volumes of data that are now collected in the factory floor, and comments about the richness and fidelity of information, both for the physical and the virtual entity. However, more important is that he identifies some different and new focus for the digital twins. I mean, you are welcome to read this white paper, if you wish, but here I summarize more or less what he points as important things, in the new focus. Michael identifies the need for lightweight kind of versions of models. So he says, don't put that much emphasis in mirroring details and all that, would like lightweight models so that we can use them for cost efficiency, for process efficiency, for things of that sort. And also this other important part, but very related, to the previous one, is in this way, the lightweight models can be used for systems kind of approach. And that as a new focus comes very, very close to what the biochemical applications are all about. You would expect 10 years, 20 years down the line that definitions, will shape up. But if you review the literature, there's an abundance of definitions from academic community, from industry, from reference kind of engines, all very different from each other. At first, literal meaning of digital twin appears to be simple, but actual definition is still a subject of debate. There is a consensus about the three entities that they introduce, virtual, physical, and the communication between these two, but there is also a consensus that the definition is quite domain specific. And why we don't have a definition, apparently because the technology is fast evolving, and as we said, because it is so much context related or so much domain related. And this is an indication that us as context, knowledge, experts have an upper hand or priority or responsibility to define the concept in our own domain. So what kind of things may differentiate these digital twins as you go from one domain to another? One is a list of things I have here. The complexity of the physical asset itself is the way that you can collect or reuse data, is the valuation metrics, is how feasible it is to implement this kind of two-way communication, is the interoperability. More or less all this suggests, that we need to take charge of the digital twins itself. So let's see what we have in front of us. A bioreactor, again, is an engineering vessel and is also a biological system. So already we have two systems in place. So already we have the systems approach, and each one of them, based on a definition of grids, should have a physical entity and a virtual entity. So for the physical entity, the virtual entity of the engineering vessel, we have equations. These can be commercial, can be open source, it can be data from thermodynamics, from transport properties, from wherever. On the other side, you have a biological system, has its own models, the FPAs, the TFAs. They also have omics. They also have an abundance of information to exploit. And of course, you have a need to communicate. This is high priority to communicate and address the interactions between these two systems. But before we go any further, it may be useful to remind ourselves why we want digital twins for bioreactors. Okay, I mean, from the physical system point of view, you want to improve process efficiency. Remember the words of Greaves, in his revised white paper. We also want to prevent unwelcome changes to a very sensitive process. We want to close the gaps between the different subsystems and understand things better. From the virtual system, we have similar kind of challenges. We have modeling technology, which is going rooted 100 years back. So we want to make better use of the data. So we believe that there's an abundance of data that we did not explore. These are data from the floor. This is background data. And we believe that machine learning and AI can be very, very useful to help us close the gaps. So is it easy? Well, the physical process, we have major challenges because we have very few volumes of data. The data are also not very reproducible. You know that as better than me, that as you take the same process from one pilot to another, the results may be very different. We also have a differentiation of biochemistry, as an abundance. But the virtual system, we have also challenges as we have to cope with the system's complexity. We have also parts of the first principles which are undiscovered and some other parts which are hidden, you may say. On top of that, we want to come up with something that we can reuse. So every time we go and implement things, we don't need to start all over again. Now, concerning the state of the art, in this case, we have last year, Antonio Sanona, who gave us nice work that he's doing using machine learning and AI on systems kinetics. Antonio was candid and honest enough, didn't use even the word digital twins because apparently, there were not digital twin kind of developments behind that. However, there have been nice work, useful work, that, however, was not generic enough in the way we want. Companies are interested in that, of course they are. Companies like GEA or ANSYS, they even postulate they have bioreactors. What they have instead of bioreactors, well, they have the experimental digital twins, we have mentioned before, which are essentially case-specific kind of things. So, and with full honesty, I believe that our partner Siemens, has much better developments that they didn't even call digital twins, that they match the quality and even better than the ones that you see in front of you. So let's see what is this kind of expectation and ambition that we have built up in this project, and how we achieve that. First of all, in our case, we have a much larger picture. We have an ambition to address a methodology that involves design, build, test, learning kind of science cycles. So we're talking about different domains, that if they are connected with each other in a proper way, they can accelerate innovations, in this particular area. But we know that these areas are fragmented, and we believe that they can be connected with each other using machine learning and AI. So one hope would be that you have digital twins for the bioreactors, then digital twins for the biochemistries, and then you have pilots where you can validate all these kind of nice things, and develop, digital twins, for the entire process. Now, when it comes, however, so one is we have a big picture, the DBTL. The other kind of challenge is that we want generic methodology that we can use as a service. Yeah. So we'd like something, that can be set up, capitalizing on previous knowledge, not having to redo the whole thing again. In this way, we have also related to that is our promise in this bioindustry to develop self-regulated, autonomous kind of systems that would work as a whole, as a digital twin. And okay, so trying to formulate the methodology, we figure out we have the models on the left, we have the data on the right, and we can build digital twins in a number of ways. We can build the digital twins in the easiest way, which would be just to capitalize on data themselves, agnostic, as we have heard a number of times. Yeah. But we have very few data to claim you have a digital twin on this basis. Also, how much you believe it's utopian to believe that out of few data, you can connect with the difficult and hidden type of dynamics of the biological cell. The other option is to connect models with data, so this hybrid kind of models, where you can use a scaffold to build from a model, the digital twin. And more or less, this gives, an outline of what we have promised to deliver in this project. In other words, start from a scaffold. The scaffold is a generic, undefined kind of model that is awaiting for things to fill in. Once we have data from a process, then this upgrades into a digital saddle with predictability, and later on, reverse engineering, the information, a digital twin. So this is the whole idea. And then I will try to illustrate a number of things here together with you on open systems first, where we just take predictability and nothing else. Then I will talk a bit about data management, and then about the closed system, things that we're planning to do in the future in relation to model predictive control. So let me start with open systems, and there I would like to thank the group of Cesar, Camilo, also, everybody who has contributed, has been, very easy to communicate and very open to communicate. So all of our illustration cases more or less are based, from this collaboration. We're gonna talk about batch reactors, semi-batch reactors, and reactors which phase, have different phases. So a large portion of what you may you will find, in biochemical applications, and we'll have to cope with the very limited data. Of course, if data are plentiful and more, then we will work with these ones as well. Technology that we're going to use in the majority of the problems is physics or process, you may call it, informed neural networks. I can talk about details, in the question time. Let me go directly to the problem itself. So the first one is, again, this is a problem, a problem where you need to, a process, you want to produce recombinant proteins that produce antivenom for scorpion stings. So these are the data from the lab, and we want to train a model on the basis of that. Now, if you take a conventional approach to this thing, then a regression model, what it will do some polynomial regression, some hybrid ANNs for the kinetics, will come up with some fixed parameters for the process. And some comments we need to remember here. First, these kind of models would need a full trajectory and story of the system before they do anything. This is a fixed set of kinetic parameters. In other words, we get into a single kind of value of the parameters. And these kind of parameters, once you train the system, forget anything. So basically, they forget all the training, process that is behind. Let's see how the twinning may be different in the case of such a reactor. So for us now, the knowledge scaffold, you may say, or the starting point is this set of equations. Where we are on a blank page. We're on a blank page that is more or less with the knowledge as I saw in the scaffold, and is waiting for data. So let's drop some data here. And just two data. Then you see in the right corner, we have here. We have already a set of parameters. Set of parameters for two data. How much you can regress? You can claim a model on the basis of that. Well, you have to remember, it's not just the data; it's also the scaffold, the knowledge domain that counts for that. So how good a model could be with two data? Okay, let's check it. So let's say we take the two models and two-point data, to predict the third point, and we see that our experiments is very close. And as we continue further and further, we'll see that this goes and improves, and then are already there. So it goes and improves as we go on, but more or less, even with this limited type of information, then we have a model for a system. You have noticed that in the movie as it ran, the parameters are also changing. So as you drop things into the system, you have a new kind of value for the parameters. So you have a sequence of the parameters. Rather than you have fixed values for the parameters, you have functions of the parameters that may hide some information that you can explore. Interesting to know that, unlike what other people have said, we have made the twinning possible with a very small number of data, And this is very important for the biochemical process. At the same time, we generate, as we said, these digital threads that are exploited. Okay, how about we just predicted 1 point? How about we are predicting a little bit more for the future of the process? Let's go back to the movie, the 2 points. Now we're gonna show the points, the real life experiments, for which the model knows nothing about. And now with a two kind of point model, I will predict the future for the whole process. And this is how the future, the crosses show us predictions. You will see that they are reasonably close to the future points up to the end of the experiment. Continues like that and finishes like that. So as somebody still there, we have also made longer-term predictions, pretty good. At the same time, we are creating new digital threads, which are the predictions that you can exploit in a number of ways. In the way we described before, I have a silly kind of demonstration, illustration, how you can exploit, say by checking the quality of the data. How you can check the quality of the data out of the digital threads. Let's go back again, and then show the prediction for the 2 points. As I go to the third point, you may notice that the prediction is a little bit far away. And if I continue with other points as they go on, you will see that although the other predictions were very consistent with each other, this third point appears to deviate from the others. So this may be an indication that this third point, should be tested for quality control. I'm not saying that these threads should be checked for this one. I'm not saying that data quality should be checked only on this, but that is an illustration. It's time to move to another now application, which is the semi-batch reactor. Semi-batch reactor is more or less in concept very similar, but then we have these continuous kind of interventions into the system as we add feed in at different stages of the experiment. So the details about the feed are shown here. A polynomial or an ANN system, regression system, will give you again a fixed set of parameters. Remember, again, it's fixed, and they need to know all the story of the experiment before they fit it. And as they fit it, you may notice that as you cross from one kind of fed batch to another stage, from one kind of intervention to another, the error has increased. Doesn't show so well in the picture, but shows well if I had shown the numbers. So again, the regression model again needs a full knowledge, and we have larger errors than before. So how we do with the twinning system? Again, as before, we don't we start with just 2 points, and then we continue, and as we continue, see more or less predicted and actual values are very close to each other. Indeed, are much better than before. Even as you cross this kind of line where you discontinuously change the state from one case to another, you jump from one state to another, the model is doing very well. It's doing much better, than the previous model you've seen, and continues like that as it crosses the other things, the other bounds as well. So we have introduced this one in this continuous system, and the system performs quite well. Why is that? Because it has the support of the scaffold. The scaffold has full knowledge of the state space. So as you jump from one place to another, whereas the regression model doesn't cope with that, this particular kind of approach does. Now let me change the gear into something else. I mean, so far I was showing all these scaffolds, which we knew that they were this kind of scaffolds. We knew we had a batch reactor. We knew we had a fed batch reactor. But what if we don't have a scaffold? Or what if we have different phases in the development of the scaffold? I mean, you would expect a biochemical system to have this one as any kind of organism. If you build a differential equation for yourself, you would expect that the differential equation, if you are an infant, is different from what you are mature or what you are, grown up or, around the time of your death. So the differential equations for a biochemical system should and could adjust as time goes on. So two different variations of what we have seen before. One, I don't have a scaffold. The second one, I have different phases in the differential equation. In other words, my set of differential equations, what I call scaffold, is changing as I move from one domain to another. So that brings me to another illustration. This is an induction kind of version, extension of the problems I had before. So we have a growth phase, we have an induction phase. So in this induction phase, we don't know exactly. It's not a scaffold, it's a matrix of scaffolds. And then you see this orange kind of box has now equations that we are not sure about. Even now for regression exercises, this is a task because you need to fit not in a kinetic model, but into variations of kinetic models. And it has taken about a month and a half for one of my best, dissertation students to come up with all these different regression models that are available. Instead, you can use a twinning in a different context. You can have options for models, model A, model B, that you will test as they can cope with experimental data. And here I have to say that this kind of part is not part of bioindustry, but it was driven, for us by curiosity. So a good number of everything, actually, from the illustrations I show and share with you, is more or less incomplete kind of research that involves experimentation, that we do with experiments. So we have two models here, model A and model B. Let me go back. We have used also a classification function that identifies a good model. Way part start, sorry. Both models start average and they continue average. And one model becomes model worse than B, sorry. They both become, and then in the end, last model, this can extend, with a large number of kinetic models. Also, it can be adjusted to account for different phases. I was not showing, different equations for different phases, but different models for the system. And as we will see a little bit later, it can be a nice link with kinetics of the cell. So let me stop about illustrations here and make some note about managing, capitalizing data that come out of this exercise. Recall remember what we have as a procedure. We have a scaffold, which are these models, and some data that come from the experiments. And then out of the experiments, we embed data into models to come up with digital twins and digital shadows. Now, these digital twins themselves have become or can become part of, or you may use new scaffolds to use. So these upgraded scaffolds themselves, or let me put it in the other way, the digital twins themselves can be seen as upgraded scaffolds in the future. Also, both scaffolds, the upgraded scaffolds and digital twins, can be used as starting point for generative AI applications. So we can use these ones, to do other rounds of
Antonis, we've lost you.
Come up with this kind of okay.
So very sorry, Anthony seems to have an internet connection problem.
Yes, he's coming back.
You back, Anthony?
Let me know which part you lost me.
Go back a couple of slides, I would say. Yeah, here. Yeah.
Okay, so here I was trying to remind you. This was managing that. So at this point, I'm leaving illustration. So I'm trying to say a few things about the data that we're using and generating. So at the beginning, we have the scaffolds. These are the data that we have. These are models. These are data. Yeah. And through the experiments, that we integrate with, we come up with digital shadows and digital twins. And what I was about to say was that the scaffolds themselves have been upgraded digital twins, which themselves, as upgraded scaffolds, can be used as scaffolds in the future. So this is one part. The other one is that then the upgraded scaffolds and digital twins, are actually nice, excellent basis to apply generative AI. So can generate and mimic, on the basis of a more reliable system, other things in the process. And I was saying also that this kind of simple picture hides the workflows, hides the machine learning algorithms, all this work that is behind the applications that I was showing. And it's, apparently more thinking there, the group of Athena, since they have set up this diagram that shows, the connections, between models and data and workflows in this virtual factory, scheme that they kindly share with us. Apparently, semantics have an important and critical role, yeah. But as I keep on saying, I favor ontologies and semantics, but all provided that they bring enough attention to the context, not just reuse, experience from other applications. At this point, let me touch on this other topic, optimization and control. I understand that the audience is not necessarily familiar with control, so I share some introduction to control. The most conventional way to control things, the feedback PID controller, essentially, is very successful, very accepted, very stable type of control, and automatically adjusts input to output. But the advent of models have enabled a much better application, very popular with industry, the model predictive control. So a model here, is connected with a controller to build an MPC. So you see that the process and the MPC are connected like this two-block diagram with each other. So contrast to the PID, the MPC predicts future behavior and optimizes future behavior. So in other words, it doesn't just adjust, but optimize the response. So the MPC itself, how it works. I mean, the MPC is selecting the input variables or the manipulated variables so that they match a desired output. And itself, it is a two blocks. One is the model itself, and the other one is the optimization itself. So this is the structure of MPC, yeah? And again, the value of the MPC is that it is the power to predict, the performance of a system, yeah? But how sophisticated are the models behind that? So again, it's part of the background material. I mean, an MPC would work in a rolling receding horizon, and uses linear kind of equations to predict the future input and the future output from changes in the manipulated variables using linear models that are retrained at each iteration. How, in contrast, the digital twin is capable to manage much larger sets of data, and it has excellent predictive capabilities that we have already seen in the illustrations before. Now, in the conventional MPC, this is converted to an optimization problem where the things in the past are given, and we want to optimize the future essentially in terms of the manipulated variable so that to optimize that. A digital twin can apparently mimic and build on this experience, and actually can, because of the richness of the data, involve much more sophisticated solutions to optimization. The other thing is that the MPC is quite successful because it is also quick, yeah? And a digital twin should learn from that and try to explore model reductions, we haven't started that, so that it can be efficient in computing time and computing efficiency. And because, again, of the richness of the model, it can involve not just one objective, but additional KPIs as well. And as a conventional MPC rolls in time, the new set of data replaces the old set of data, yeah, but no memory, the memory is lost. In our particular case, as in this twin, as we move from one iteration to another iteration, we make the model richer because we embed more and better models. So we improve the model and we keep the memory. And this memory, again, for a digital twin-based kind of system, could come up with other type of more sophisticated controls, also the falsification of things for which we don't have reliable input-output performance. So I'm borrowing this nice picture from my friend Vitor here to explain more or less the options or the potential for additional layers of control that we can build in such a system. And this could deliver the self-regulated autonomous promise that we have in the bioindustry. And this is more or less this part. But on top of that, we can go on, following Griff's kind of encouragement, to come up with networks of digital twins by forms of decentralized control, as I saw here, or distributed control, or federated, or you may say supervisory type of control. In other words, use them in the systems approaches, networks in this case. Or we can involve through the falsification the things that we are not sure about, which is more or less the biochemistry, which is the biological system. This in the short term will give you set points, will give you input-output relations. In the long term, it can give you suggestions on how to readjust, redesign the biological strain. So time to touch on biological strains, I guess, now. So far we have seen the engineering part. Now time to see the biological part. In the biological part, the virtual assets involve the models we have, involve the data. And although we have an abundance, options for data, our models are not exactly the kind of models we have for engineering process. And the closest one that comes into a model are the genome scale models, yeah? But let us pay a little bit attention of what the genome scales are all about. There's a lot of confusion about GSMs and what they stand for. And there is still literature as we speak that identifies these models as simulation models, which is so wrong, because these models are doing convex analysis. They just build, some sort of polyhedron around the solutions that we don't know how they perform. So we don't have information about the kinetics. We have an underdefined system. In other words, a system where we can arbitrarily set up parameters and come up with a version of the solution. How many of these kind of scenarios we can build? I give you here some ideas about 3 biological systems. This is the number of reactions, number of metabolites, and the number of permutations that relate to this one. So a brute force approach to generate instances from this kind of permutation is apparently utopia. What we have instead is an alternative approach that I will explain to you and also show some results. The alternative approach is, first of all, to reduce the space as you want, so you don't have this kind of convex analysis that you had in the GSM, but something smaller, yeah? And after you make it as small as you can, then you sample the space. You generate a very large number of points, and then you screen them using 2 important criteria, which is process efficiency and stability. You come up with a smaller number, and then you apply machine learning kind of techniques and AI to come up with clusters of solutions that you can analyze further. Let me show that in slides. So the first one, you can use a literature data to build a GSM model. You can, we are actually following an Oracle approach by my colleague Hajmanitakis from EPFL. So after that, you build a TFA, thermodynamic analysis model, and you apply extended linear programming to reduce the reactions into a much smaller set. Well, after you do that, as we said, you sample the space. And here, the red kind of parameters are the ones you sample, and the green one is the one that comes from thermodynamics. So you sample with 2 different kind of criteria. One is the efficiency of the metabolomic flux, and the other one is stability, where the different options are checked in an approximate way only on the basis of the eigenvalues. So you do these ones, and then you apply AI and machine learning to analyze the different sets of data that come available. And here I show, how this can be used, in order to screen these large populations and come up with a solution. But I think a better one is to have an example around that. So this is an example also from our project, is production of muconic acid. The metabolic network is shown on the left. So we have some data that we use, as a starting point. And then you see that TFA and has reduced and the number of reactions, into a much smaller set. When it comes to efficiency, metabolomic efficiency, you see the analysis as it takes the initial efficiency from the left to the right, essentially enabling kinetics that build, something identifiable as a product. And then on the other side, you have the results from stability with different levels of perturbation. Decision trees were used here in order to identify different models with respect to their stability on the different permutations. So you have somehow, a decision tree for that. And you can apply, develop, an analysis with different kind of AI methods, or you can combine all of them with significant accelerations, as you see in the last kind of highlighted result that I have on the right. The most exciting part, is that through this analysis, you can identify the enzymes which have the highest impact in the overall metabolomic kind of way. Here we have identified 20 enzymes, and the impact of the perturbations, have broad emphasis for the kind of enzymes that need to be analyzed further into this list that I have there. I think it's time to conclude because there is a strict, deadline by Michael. I want to more or less summarize some of the points. Bioreactor digital twins, as I said, is a concept that falls in our own hands. We shouldn't expect someone else to define it for us. Yeah. In my view, there is a lot of promising preliminary evidence that enables twinning to take place with very limited information. I think we have created a concept which is different from what you will find, and it is something which can function as a service, which is something we wanted to have. We haven't done work on closed systems yet, but the kind of work or technology we apply, which is PINGS, is known to perform very well in reverse engineering ANNs. So we are hopeful for this part. And again, we have, I think, established a line of communication, very distant, but we have established a line of communication with the biochemical process. No, in my presentation, I talk about knowledge, I talk about intelligence, I haven't talked about wisdom, yeah? So I thought to close with a quote on wisdom. So the one that we're more familiar in Greece is this one, yeah? The only wisdom is that we know nothing. But we don't want to close this presentation with such a pessimistic kind of approach. So let's try something more optimistic and more poetic. So I would close this presentation with this one. Knowledge is proud that it knows so much, and wisdom is humble that it knows no more. So with all that, I would like to share my acknowledgement to this group of people that are behind everything I have seen. I just present their own work. Thank you very much.